Hello, I'm Putu Arindra from Mechanical Engineering Udayana University. Now we will now we will discuss about discovering metal or historical overview. And my main reference is a book metallurgy for the non-metallurgy. Now we continue to chapter 4.1. A native metal 4.1. Most metals naturally occur as mineral or compounds. The metal atom have reached the other metal or with non-metallic atom. One of the primary tasks of the metallurgy is to extract the metal from the compound. The few metals that are found in an unrich state and termed native metal. Through the use of native metal, the science of metallurgy has born. The Chalcolithic period is the name that archaeologists give to the time period that immediately precedes the Bronze Age, in which metals were first being mastered, and they date this period between approximately 5000 and 3000 BC. Ancient men first used native or natural occur and relatively pure metals such as gold, silver, and copper. Nuggets of gold could be found mixed with the quartz sand of riverbed in many areas of the world. Such gold nuggets were hammered into decorative shapes, but because of the low strength, the metal was useless as a weapon or tool. Gold was shiny, lustrous, and even as today, useful for jewelry and prized for possession. Silver, which was much less common, also was used in a similar fashion. Even the naturally occurring alloy that were mixture of silver and gold served no practical purpose. Historians frequently refer to the Copper Age as a precursor to the Bronze Age. The use of copper gave birth to this first practical age of metallurgy. Copper, like gold and silver, exist in a native or natural state. Ores that were more than 99.9% pure were found in many parts of the world. Some civilizations, such as the mound building Indians of the Ohio Plains, found or trade for native copper. The copper metal was most commonly used for ornament purpose, hammered into decorative shapes and used as jewelry and to line burial sites of important citizens. There are few examples of copper spare points found in North America, but most of the copper was used for ornament. Other civilizations, such as those in Egypt and the Middle East, know that copper hardened and strengthened significantly when hammered. Although the term nanotechnology was clearly not used, this Asian metallurgy were hammering to control the number of configuration of the nanocrystalline element of the structure of copper. The hardened copper became useful as a tool, and thus the Copper Age was born. Knife could be fabricated for agricultural use and for cutting the flesh of fish and game. However, such knives were generally used less for the penetration of hides or the cutting of bones. Thus, although copper knives serve a purpose, they lack the strength to serve as effective weapon. The discovery that copper could be obtained by heating conflict, malachite, and other bright blue stone or mineral was made between 4000 and 3000 BC. This was the primarily copper sulfide ores, and ores is a natural mineral that can be mined and traded for the extraction of any of its component and metallic or otherwise. The metallic component of copper sulfide mineral is copper. Sulfur is one of the non-metallic elements. Extraction of copper from copper sulfide ores provide achievement with another source of copper. Once extraction technique was developed and the use of native metal was not restricted, the transition from hammering pieces of native copper into a desired shape to extraction of copper from copper sulfide mineral required both high temperature and significant insight. There is a little doubt that the discovery that copper could be extracted from copper sulfide was not made in a deliberate quest for copper. Soaking copper resulted when a fire was boiled beside an ore deposit. Others suggest copper was produced by chemical reaction in the early pottery kilns. However, in spite of the accidental nature of the discovery, this early extractive metallurgy must be given credit for their power of observation. Metal, specifically copper, could be won from ores by the application of heat. In this case, the heat of the wood and charcoal fire. Extracting copper from its ore is not an easy task. First, the metallurgy must heat the ores to temperature over 982 degrees Celsius, not an easy task with a wood fire. And second, the metallurgists need something to contain the molten copper. As a true experimental, how would you accomplish either of these tasks without access to modern technology or materials? The ancient metallurgy was aware of two important metallurgical facts. First, that the strength of a metal could be increased by hammering, and second, that metal could be extracted from ores. The process of hammering or forging is frequently termed cold working. If the process shaping was conducted at elevated temperature, the strength of copper was not significantly increased. Thus, metal fabricated at elevated temperature had different properties and the metal fabricated at low temperature. This difference in the behavior of a metal process at elevated temperature and that of a metal process at near ambient or room temperature remain an important factor in the shaping of metal and alloy today. The observation that metal could be extracted from ore was vital to the development of metallurgy because the number of supply of native metal was quite limited. Before metallurgy could emerge as an art of science, the ancient metallurgists had to be aware that the supply of raw material was not limited to the native metals. The development of high temperature to melt copper also expand the amount of material available. Large pieces of copper could not be cut and therefore was not significant importance until melting technique become available. And the next to 4.2, the Bronze Age. The Bronze Age began when it was discovered of mixture of two metals or alloy were stronger than either of the metals taken individually. This discovery was probably made about the same time that extractive metallurgy was discovered. The discovery that tin alloy addition strengthened copper was the crux of the Bronze Age. A chemical of analysis of the typical bronze alloy from the Asian Middle East show that the alloy contained approximately 87% copper, 10 to the 11% tin, and small amount of iron, nickel, lead, arsenic, and antimony. It is rather startling to realize that approximately 4,000 to 5,000 years passed between the advent of the Bronze Age and the development of sterling silver, a more modern application of the strengthening effect of alloy addition. Sterling discovered that the strength of the silver could be improved greatly by the addition of small amount of copper. The small addition of approximately 7.5% do not affect the appearance but significantly improve the serviceability of silver vessels, jewelry, and utensils. Even more startling may be persistence of Asian metallurgy practiced into a relatively modern times. An 11th century description of the bronze state that is an alloy consisting of the 1 pound of copper and 2 ounces of tin. This alloy remarkably similar to the X87 of Cu found in the Asian bronze. Other publications suggest that a soft bronze or gunmetal is formed when 60 parts of copper are mixed with the 1 part of tin, and that a hardened gunmetal such as was used for bronze ordnance is formed when the proportion of tin is approximately double. The hardened gunmetal contains 88% of Cu. The historical evolution of metallurgy practice from the production of copper to the production of bronze is difficult to trace. Many of the early attempts to produce copper by heating copper sulfide ores in the presence of red-hot charcoal produced the arsenic-containing copper alloy. The material ergite are frequently found with other copper sulfide ores, and the reduction of the minerals would provide arsenic as well as copper. Such copper are significantly stronger than arsenic-free copper. This first copper tin bronze probably result from the accidental annihilation of alloy element through the press in one body. Okay, from the technological viewpoint, accidental improvement of property of metal is far different than the intentional mixing of two or more ores or refined metal to obtain an alloy with specific desired property. However, by 3000 BC, Asian metallurgy had learned to intentionally mix ores of copper and tin to produce bronze that is very similar in composition of some modern alloy. The alloy that were made from intentionally mixed or make the real onset of the Bronze Age. Mankind now had a metallic alloy that could be cast or forged to shape. Bronze was significantly stronger than relative pure copper and was useful both as a tool and as a weapon. This instinct is an example of the high level of perfection achieved in Chinese foundry technology in 7th century BC. The bronze in this casting contained less tin than was typically of bronze weapon from the same era. The tin bronze was probably produced because of the difficulty in locating good supply of tin. tin-rich ore were not as common as copper-rich ores. Frequently, tin had to be transported over large distance. Because of this problem, bronze was an expensive material, and unalloyed copper was probably used whenever practical. The metals for use in farming and domestic quarter did not require strength as high as the metal for use in hunting and fighting. Even during the Bronze Age, these were materials strong edge, and tin was a critical material. 4.3 Making metal extractive practices. The most metallic element occurs naturally as a mineral or ores, which are compounds that result from a reaction between metallic and non-metallic atoms. Most copper, zinc, and lead ores are sulfide, while iron and aluminum generally found in oxide ores. Mineral and frequently brightly colored, iridescent and attractive because of such attractive Asian men collect mineral sample. For example, a typical copper containing sulfide mineral is bornite, which contains copper, iron, and sulfur in the ratio of 5 copper atom to 1 iron atom to 4 sulfur atom, designed as Cu5FeS4. This ore is reddish purple when freshly broken and becomes iridescent blue or blue-green when exposed to the atmosphere. This change of color results from the chemical reaction of the ores with oxygen in the atmosphere. Chalcopyrite is a yellow copper sulfide ores that also contain iron, while cophlite is a deep blue copper ores that contain only copper and sulfur. Extraction of metal from their respective ores requires work or energy to separate the metal from the sulfur or oxygen. This energy can be supplied in the form of heat, and the first extraction were probably accidental. A fire got out of hand, and mineral samples that had been collected for their beauty were hid, resulting in copper metal. A fire was pulled near or against a copper sulfide mineral deposit, and copper was produced. Or it is even possible that during an act of worship, an Asian man intentionally cast bring stone into a fire and subsequently found that the gods had turned to the stone into copper metal. Pyrometallurgy is the extraction of metal from ores by chemical reaction at high temperature in fuel-fired furnace. Pyrometallurgy may involve roasting and or smelting for the extraction of refinement of metal. Smelting refers to melting process that separate metal in fuse from non-metallic material. Other more modern methods of extraction and refinement include hydrometallurgy and electrometallurgy. Hydrometallurgy is the leaching of removal of the metal from the ore body by passing a strongly acidic or alkaline solution over the ores. Electrometallurgy involves the extraction of metal from their ores by the application of large amount of electrical energy. Experimentation with copper smelting began in the Chalcolithic period at the same time after the melting of copper was discovered. As the supply of native copper, readily available copper sulfide ore was depleted, the metallurgist was forced to to turn to the extraction of metal from other ores deposit to obtain a supply of copper. The extraction of copper from the copper sulfide ores and from the other ores deposit required that the early metallurgy refers a reaction that had occurred between copper and another element found in the earth crust. Melting of copper also resulted in the discovery of alloying and the Bronze Age. A true modern extraction products are complex. The smelting process can be very simple. For example, early North American smelters smelt lead sulfide to produce lead balls for bullet used by most colonial woodsmen. Galena is the most common lead ore, and the lead was extracted by building a fire inside a hollow tree stump and roasting the galena ores on the fire. This process results in the lead sulfide reacting with oxygen in the air to form molten lead and sulfur dioxide. A true extraction of lead from galena had been widely practiced for many years. It was not widely recognized until relatively recent time that silver is associated with lead extraction from galena. Lead sulfide ores generally contains appreciable quantities of silver, and because of the potential for silver recovery, lead smelting is currently practiced under very controlled conditions. Basically, such processes are the key to any pyrometallurgical extraction process. An ore is held in the presence of selected and controlled environment. This environment treats with the ores to produce both the desired metal and the other product of the smelting reaction. To illustrate the unreversible nature of some smelting reaction products, note that hydrogen sulfide gas produced by lead smelting is poisonous. Lead smelting was successful because at temperature commonly reached in a wood fire, oxygen in the air reacts with a lead sulfide to free the lead and process both sulfur dioxide and hydrogen sulfide gas. We next to chapter 4.4, the iron. The early name for iron means stone from heaven. In several languages, this name probably resulted because the first iron used by ancient man was literally from heaven. Meteorites weigh from a few ounces to tens of tons have been falling on the earth since its beginning. The meteorites frequently contain large quantity of metallic iron, and the first iron used by ancient man was from this stone from heaven. The first iron extract from the naturally occurring iron oxide deposit could have resulted from primitive man building a wood fire at the base of some windswept cliff. If the cliff outcropping happened to be rich in iron oxide, after days or even months of use, the fire cooled and the ash contained a small amount of iron sponge. This sponge was the iron that remained after the oxygen had been removed. The iron had not been melted during its production. Like the iron in the stones from heaven, the sponge could be hammered into shape and was relatively strong. Spear, arrow tips, daggers, and other tools and weapons could be fabricated. The first iron to be developed was the wrought iron. Wrought iron can be readily forget to shape. In fact, the term wrought means to shape by hammering or beating. Wrought iron is very ductile for forging because it contains very little carbon. Carbon is an interstitial impurity that strengthens the iron lattice. In fact, the iron alloy that contains between approximately 0.1 and 2.0% carbon have a special name that is still iron smelting. As with the reduction of copper sulfide ores, the first reduction of iron oxide was probably accidental. It was the power of observation that led these ancient metallurgists, who also served as the miners, chemists, and technologists of the day, realized that the iron could be produced in simple furnace by direct carbon reduction of the oxide ores. The exact date of this first intentional reduction of iron cannot be stabilized, but it is certain that the making of shaping of iron was widespread in Egypt by 1500 BC for the next 3000 years. Technique for the production of the iron did not significantly change. Iron sponge was produced by carbon reduction of the oxide. Iron products were made by pounding the sponge. Iron oxides ores are present in many areas of the earth. Thus, roughly at the same time Asian man was reducing iron ores in Egypt, it also was being done in other areas. China, India, Africa, and Malaya served as sites for this initial development of iron making practice. It is perhaps significant that the furnace developed in this country were all quite similar. They were different in shape and size, but furnaces were functionally identical. The chemical reduction to iron occurred without smelting, and the resulting metal was relatively pure and soft. It could be hammered into useful shape and was termed wrought iron. Unlike the reduction of copper sulfide ores, full smelting of iron is not practical because higher temperature and more carefully controlled environment is needed. Smelting of iron oxide requires some carbon monoxide to react with the iron oxide to produce iron and carbon dioxide. Iron smelting, therefore, must use carbon in the form of charcoal or coke. For two purposes, the carbon must react with oxygen or burn to supply the heat necessary for the smelting operation. In this case, the carbon is serving as a fuel. However, the carbon also serves as a reduction of reacting again to free the iron from the iron oxide. The carbon reacts with the iron ore, forming carbon dioxide and iron. This furnace could easily have been developed after the first accidental reduction of iron oxide. Improved blast furnace design enable higher temperature to be reached until the temperature exceeded the melting point of the iron. The molten iron dissolved carbon and other impurities, which was not the case in the production of sponge and wrought iron. This product from the furnace that melted the iron was called pig iron. The raw material used in the production of pig iron also different from the raw material used for wrought iron. Instead of iron ore and wood, iron ore, coke, and a flux were used. The limestone aided in the formation of slag that floated on top of the iron and removed impurities from the molten iron. Because of the blast of air that was forced through the furnace became known as a blast furnace. The use of blast furnace greatly increased the rate at which iron could be produced. In such a furnace, approximately 2 units of iron ores, 1 unit of coke, 1/2 unit of limestone, and 4 units of air are required for each unit of pig iron produced. The smelting process in a blast furnace begins when the chains of ores, coke, and limestone is loaded into the top. The temperature in blast furnace are approximately 150 to 200 degrees Celsius because of a rising stream of hot carbon monoxide that results from combustion of the coke. At this temperature, the carbon monoxide begins to react with the iron ores to freeze some of the iron. At the same time, some of the carbon monoxide is cooled by the change and form carbon dioxide and free carbon. This free carbon is the shade that darkened the skies over iron producing cities from the 60s to the mid-20th centuries. Removal of this soot from the rising blast is difficult and represent an ever-present problem common to the production of metal from their ores. The control of production practice to produce high-quality product without the contamination of the environment is a relatively modern innovation. Environmental contamination was not considered a problem until recently. However, the production of soot was well known as which is drawing of an early version of the blast furnace. This drawing appeared in Georgius Agricola books de Re Metallica, which was prepared in 1556 and translated from Latin into English by Herbert Hoover and his wife, Lo Henry Hoover. The pig iron produced in a blast furnace has the advantage of the rapidly produced, but pig iron is very hard and brittle due to high level of carbon. Wrought iron is ductile and true but has little strength, while pig iron is strong but brittle and lacks of toughness to withstand sudden blows without breaking. In fact, the cast bar of pig iron sword would shatter if it was hit against a tree. The reason for this difference in behavior is mainly due to the potent strengthening effect of carbon in iron. Wrought iron is a highly refined metallic iron that contains relatively uniform, distributed, insoluble, non-metallic particle. The individual particles are termed inclusion to approximately 1 to 4% of the volume, and any wrought iron sample in inclusion, typically a typical chemical analysis of wrought iron show the presence of very little carbon, silicon, and other elements found in pig iron. Unlike wrought iron, the lack of purity in pig iron makes it hard and brittle. This brittleness makes pig iron difficult to shape by hammering or forging technique. However, pig iron can be cast. In fact, carbon level of pig iron approach the melting point of 4.30% carbon in the iron carbon system. In the iron carbon system, melting composite result in a melting point of 1140 degrees Celsius. This is much lower than the melting point of pure iron. And next steel, which are iron containing between approximately 0.1 and 2% Celsius, 2% carbon, combine the toughness of rock iron with the strength of pig iron. Steel can be made from rock iron by heating the iron from a long period of time in a red-hot charcoal fire. The hot iron absorbs carbon from the charcoal so that the carbon atom diffuse into the iron lattice. The result is an iron-carbon solid solution alloy that we know as steel. The increase in carbon also provides other advantages in the strengthening of steel when it is quenched from elevated temperature. The heat is played in a major role in the early development of steel, and by the time of the writing of the Odyssey, the treatment of steel was well known to the Greeks. The blinding of Peloponnesus by Odyssey was described as when the smith plunges the hissing blade deep in the cold water, so has his eye around the olive oils. The development of steels into a material of common use was critically to his story. For example, the Celtic invasion of Italy in 223 BC was unsuccessful, partly because of the poor quality of Celtic weapon. The Romans had steel, the Celts had iron. The iron sword and the daggers easily bent, and although one man might be killed or injured if the first blow was successful, it was difficult to fight with sword that had to be strengthened between blows. The nation without steel was therefore not equipped to fight a nation with steel. Therefore, the possession of steel shaped the development of nation. 4.5 Discovery of modern metals. The use of the Latin "am" suffix in naming of metals is typical of suffix on all metal discovered in solid after 1800. Many of these "ams" metal have tremendous commercial importance, primarily because of their use as alloying element. Alloying elements are generally to improve the mechanical, electrical, or chemical property of the other metal in a fashion similar to the addition of tin to copper to improve strength. Some of the commercial use of several of the metals described subsequently. Beryllium is added to copper that improves its strength. The mechanism or process by which beryllium increases the strength of copper is very different than the strengthening that results by tin or zinc addition to copper. The copper beryllium alloy contains only a small amount of beryllium, but can be processed or heat treated to be much stronger than any low tin brass or copper zinc alloy. These very high strength copper alloy are used for the production of springs in the electrical industry and to make non-sparkling tools for use in potentially explosive atmosphere. Next, cadmium was discovered in 1817 and primarily found in zinc ore. Cadmium coating or plating was used to protect nuts, bolts, and other components made of high-strength steel or other relativity corrosion-prone metals. The cadmium plating acts much like some paints and limits the access of the environment to the protect component. Many of the components in commercial aircraft are cadmium. Cadmium is also an addition for some dental alloys because it increases the strength of the filling. Then the increase of strength improves the wear resistance of the filling and prolongs its life expectancy. However, cadmium had at first environmental consequence and effort to replace cadmium with an equally effective coating are ongoing. Chromium was discovered in 1798 and in use mainly as an alloy addition in steel production. Chromium improves the resistance of steel to oxidation of corrosion and is essential ingredients of stainless steel. Corrosion will safely limit to the utility of the steels if chromium was not added. Stainless steel contain up to 30% chromium, and although the primary function of chromium additions is to improve the corrosion or chemical behavior, chromium is a small quantities improve the strength of alloy steel. Molybdenum was discovered in 1781 and is primarily used as an alloy addition to steel. However, molybdenum melts at 2620 degrees Celsius compared to the 1535 degrees Celsius for iron. This difference is in melting temperature complicates combining of two metals into an alloy. Because of its high melting point, molybdenum, also with tungsten and rhenium, is called refractory metals. The term refractory generally applies to a wide range of ceramic materials made of SiO2, Al2O3, and other high melting point compounds. The refractory metals are not compounds, but have relatively high melting points. Because of its high melting temperature, molybdenum is used in the manufacture of high temperature heating element and furnace tray. Work to develop molybdenum alloy for gas turbine application in one of many studies designed to obtain metal and alloys for very high temperature application. Tungsten was first refined from ore in 1783 and was originally called wolframium. Tungsten was first used as the filament for the incandescent light bulb, and this use account for 15 to 20% of all tungsten use. The major use of tungsten today is in the form of tungsten carbide, which is a very hard, wear-resistant material. Carbide type drills and machine tools increase of 65 to 70% of all tungsten use and are found throughout the home and industry. It is interesting to know that tungsten, which is a very brittle, high-strength material at room temperature, can be fabricated into the fine wires required for light bulb. Vanadium is among the hardest of all relatively pure metals. It was discovered in 1830 and is actually more abundant than copper, nickel, or zinc, but it's very difficult to purify. Vanadium is primarily used as an alloy addition of steel for manufacture of woodworking and metalworking tools. Magnesium is the like of the widely used structural metals. Magnesium is more than one-third lighter than aluminum, having a density of 1.7 gram centimeter cubic compared to the 2.7 gram centimeter cubic density of aluminum. Because of its low density, magnesium has been used in aircraft frame. It is also an important alloying element in aluminum. Magnesium, however, can ignite very readily when finely divided and is actually used in flash and other pyrotechnic devices. Like many other metals, magnesium is rarely used for structural in its pure form, but become a useful structural material when alloyed with aluminum, mangan, or zinc. Titanium was discovered about 1790s, but because of the difficulty of freeing titanium from oxygen and nitrogen, it was not really available as a structural material until the 1940s. Titanium is difficult to process and to shape, but has both as high strength and low density. This gives titanium the desirable property of having a high strength to weight ratio. It is the strength to weight ratio that makes titanium alloy desirable for aircraft and spacecraft application. Because of its natural corrosion resistance, titanium is also used in the chemical process industry and for orthopedic implants. Iridium, rhodium, palladium, and platinum are, along with gold, termed the precious metals. They are all very dense and very corrosion resistant. However, the term precious metal comes from the fact that all these metals are expensive. Because of this expense, the precision of metal are used as catalysts and for applications that typically call for small quantities of material. Pen points, electrical connectors, then T3 and pivot point in fine balance are examples of use of the precious metal. Platinum iridium alloy are very resistant to food acids and are useful in dental restoration. Aluminum, the third most abundant element on the face of the earth, is a member of the family of metal that includes gallium, indium, and thallium. Aluminum was not discovered until 1825. Very pure aluminum, like copper, gold, and silver, is too soft to be of much value as a structural material. However, commercially pure aluminum and aluminum alloy with copper, silicon, magnesium, zinc, and other metals have many industrial applications and are second to steel in volume of material product commercially. Most aluminum is extracted from its ore by electrometallurgy. Because electrical energy is required for this type of extraction, it is common for aluminum produce plants to be located in areas where the electricity is inexpensive. Hence, many aluminum production plants in North America are located in the regions having less expensive hydroelectric power. Even True high quality aluminum ores are not common in that area. It is less expensive to transport the ore to the source of the energy than to transport the electricity to the source of the ores. 4.6 Refining of metals. Refining of metal refers to process that purify extract metal. Refining of metal, like the extraction of metal from ores, includes many ancient practice and more modern advance. For example, gold always occurs in a metallic state, and it can be extracted from minerals by a relatively simple means, that is, panning and sluicing. For gold effectively separate the gold from minerals because the density of gold is much higher than that of minerals. For example, the quartz in sand has density of approximately 3.2 grams centimeter cubic. And panning and slicing with water weighs away like sediment from gold nuggets or flakes. However, the remaining gold flakes or nuggets are not necessarily pure. Further purification step may be needed. Gold refining is the relatively simple process of heating the gold to a very elevated temperature. At this high temperature, most of impurities in the gold react with oxygen in the air to form metal oxides. Some of oxides formed by such reaction are gaseous and therefore carried away by the surrounding air. Other oxides are not gaseous, but the reaction to form the oxide products relatively low density compound that float on molten gold as a slag or dross. The slag float on gold is much the same manner as wood floats on water. Therefore, the gold can be refined by simply scraping the floating debris from the pool of molten metals. This technique from refining gold was known by the period of 2000 to 1000 BC. Refining technique for most metals are much more complicated but involve similar phenomena. Many techniques now used were not developed until quite recent time. Today, refining can be used to produce very pure metals: copper, gold, silver, aluminum, iron, and many other metals can be purchased at purity level of 99.99% which is equivalent to 1 part impurity in a million. Clearly, modern refining practices are excellent, and metal and alloy that are virtually free for unwanted element can now be obtained. Unfortunately, such purification is typically expensive, and most engineering alloy contain significant quantities of impurity atoms. This can be readily seen in a micrograph of commercially pure aluminum at 500 times magnification. The dark particles in the micrograph are concentration of impurity compounds. In this case, L2O3. These impurities concentration of particle are similar to inclusion of stringers in wrought iron. A true very high purity metal are typically too soft for structural application. The small amount of impurities in some commercially pure metals imparts adequate strength for some structural application. For example, commercial heat exchange for certain applications are made by commercially pure titanium. Although titanium is characterized by a somewhat low thermal conductivity, the major design factor in heat transfer relativity relates to material thickness, corrosion resistance, and surface films, not just to the thermal conductivity of the metals. For this reason, commercially pure titanium can have advantages over other metals in the design of heat exchange. It offers good strength resistance to erosion and erosion corrosion, a very thin conductivity outside surface film, and a hard, smooth surface that limits adhesion of foreign material and promotes dropwise condensation. Very high purity metals are often to solve for any types of structural application. For example, the gold that is 99.99% pure is not practical, even for use as chains or pins in jewelry. However, some modern material specifications require exceptional refining technique. Silicon used in the semiconductor industry must be produced at controlled purity level equal to and exceeding less than 1 impurity atom for every million atom of pure element. Such high purity is needed when strength is less important than other properties such as electrical conductivity. In the transistor industry, it is now common to be concerned about alloy addition and impurity level at concentration level of 1 part per billion. The concentration level is 0.0000001%. Okay, that's all from me. If you have a question, you can write below in comment section. Thank you.